today we're going to talk about the stack. The stack is one of the concepts that a lot of people don't always get right or understand completely. So this is a very basic video. We're going to start with the very basic concepts about the stack so that you can understand conceptually what the stack is, right? So to start off with, traditionally when we talk about stacks, we're essentially just talking about storing things away for a later time. So for example, if I took these books off the bookshelf here, right, and I just started stacking them up, right? Right, so got a big stack here now, and if I want to read them, I take them off the stack, and then I go and read them. If I want to read this version, this one down here, that's all the way down here, I have to essentially pop all these off the stack and then get to this book. I can't just essentially pick it up and read it, right? And I can't really read it while it's on the stack. So that would be, you know, your traditional implementation of a stack and how people really think of it. But stacks aren't always like that. You can create a stack that's usable. In fact, you can create a stack that's really only usable while it's been stacked. So for example, a stack of weights. You stack the weights on top of each other, and that's when you actually use them as a whole unit together. You can not be able to see over something, so you stack up a bunch of boards or something and put your chair on top of it, and you use the chair while it's on top of the stack. So the thing on top of the stack is usable. Well, you can't really get anything out of the under, you know, can't really use the board, take it out, start using it for something, but you know, essentially what's on top of the stack is usable. So I want, and this concept here about the stack being usable while it's on the stack is what I want to essentially start off with, because a lot of times I ask people about how parameters are passed and how do you get to the parameters. The first thing they tell me is you pop it off the stack, and that's not what a function stack is. That's how it's used. It's not how it's used. So I have my old whiteboard here. So that is, like I said, the traditional stack, but I wanted to show you some other use cases of a stack where, you know, you can use a stack while it's stacked. So now there's two main concepts we need to talk about first. The first one is context. I'm gonna really spell this out because people don't like my shorthand pretending I'm writing. I don't know if you can see that from there, but context. Second thing we want to talk about is something called Scratchpad. Right? So context. So let's say I came over your house and I sat down, I said, hey, what's going on? Then I said, and then they gave me $5. That's all I say. You'd be like, okay, what does that mean? What's going on, right? There's no context, okay? Now, if I said, okay, well, I bought a lottery ticket. I didn't know how much I was going to win. I knew I won, but I wasn't sure. So I took it into the convenience store. I handed them my ticket. Then they gave me $5. So you might be thinking, okay, well, he got $5 from the lottery, so he probably broke even. Now another thing I could say is, well, I was going to the bank the other day, and you know, I was trying to get $15 out of my bank. So I wrote down, went up to the teller, and you know, she gave me my money. I walked away. I realized I only had $10. So I went back, told her that I only got $10, and then she gave me $5. So I got my full 15. Now you might be thinking, okay, so the teller made a mistake, and you went back and you were able to get your full money you asked for. Now I can also say, you know, I was downtown the other day. I was in this alley, and I pulled up my gun. I said, give me all the money in your wallet. And then they gave me $5. Okay, so that one there is, you're probably just like, what the hell, is that robbing people in the alley? So context matters because you come up with a different conclusion or a different result based on the context, right? And so discuss about that when it comes to functions, right? So if I had a function called add and multiply, and with this function, it'll take parameters a, b, and c. And all this function will do is it will take a plus b, puts it into temp variable z, then it takes z, multiplies it by c, puts it into a temp variable y, and then it returns y. Why I wrote this all out shorthand here, long ways, you'll understand in a minute. So if I passed in 1, 1, 2, it will take 1 plus 1, you get 2, then multiply by 2, get 4, return 4. So with this context of 1, 2, 3, or 1, 1, and 2, I get 4. Now if I change the context, and I say 2, 2, and 3, so now it'll add 2 and 2 together. I get 4. I take 4, multiply by 3, and then I will get 12 as the result. So based on passing in a different context to this function, it processes the information and gives you a different conclusion, a different result. Comes to a different result based on the context. So we're going to get back to this problem in a minute here. But the next thing I want to talk about is Scratchpad. So Scratchpad is kind of like a little notebook where you write something down temporarily to go and do something. So for example, if I would have asked you to do these, maybe you come over here, you'll say, okay, well, 2 plus 2 is equal to 4. And you'll take 4, you multiply it by 3, and get 12. And you'll tell me the answer is 12. What will you do with this paper? You'd probably throw it away. You're not going to save it. That's your Scratchpad. If I go to the grocery store, I'm going to have a grocery list of all the groceries I want to buy. And as I go to the grocery store and pick them in my cart, I'm going to cross them out. Now, when I'm done, I come home, the result of my context of the grocery list is I have the result of the groceries. Now, I'm not going to frame that grocery list on the wall. Instead, I'm going to throw it away. I'm done with it. It's scratch paper. It's Scratchpad, right? So that's the concept of Scratchpad. So now let's bring all this back together. So your stack is the function's context and the function's Scratchpad. Okay? Now, let's find my eraser here. Have an eraser? There it is. So let's start putting this together. So we have a context. Context creates the input to which you come up with the result. The Scratchpad is where you think about that result, your scratch space of where you write down information, everything, which is also your context, and then you come up with the result. So for example, let's say you went to the grocery store, you started crossing out your grocery list, and then I called you for an emergency to come home or something. So now you have your cross the grocery list, you have your groceries that you're going to buy, and so maybe you buy them, maybe you don't, maybe you ask the grocery store to hold them. You go do something else, and you come back. Now when you come back, you have your grocery list, which is your context. So your context was saved before you went to do something else. You came back to your context, you're able to continue where you left off in grocery shop. What happens if you lost your context? You just start over. Or you end up with a corrupted context, right? So let's get to how this fits into this thing here. So the stack is essentially your scratch pad and your context. And this is how that works, right? So if I call function A will take some input from up here, and then it'll reserve some space on the stack. And so this will be your current stack location. This current space in your stack would be the scratch pad. Because when I return, I destroy that information there. That's where I'm going to do my calculations. So these local variables, you don't save them. When you return, you throw them away. So when I come in with my input, in this function here, I'm going to do a plus b, which in this case, if it's 1, 1, I'm going to store 2 and z on my scratch pad here. And now let's say that in between this, I did a function call to something else. That function b is going to reserve the next location here. Now this is inactive. So this whole location is inactive now, right? You're not going to execute that function, but it's preserved in time. It's like grocery list, right? You were interrupted shopping, and now you have this stack location frozen in time. No one's popping anything off, right? So we're just going to freeze that entire location. That is two things. That is your scratch pad, because when you're done, you're going to throw it away, but it's also your context. So right now, when I come back, I need to remember 2 so I can do the second problem, right? Because I've made a function call in between these two problems here. And so when I come back, I'm going to get 2. And I'm going to know to put it here into the second equation. I'm going to also have the context of 2 of the input, right? Because I had 1, 1, 2. And I have 2 as the result of 1, 1. Now I don't need 1, 1 anymore, so I could have overwrote them already, who knows. But I come down to here, and now this guy's the active location on the stack. So this is the active context, you could say. So the last, the very bottom of the stack of where the current function executing is the active context. And the active context is not popping and pushing things on the stack all the time. Well, we'll get to that in a minute, but it's essentially this whole range that's now active. You can consider this active. He doesn't have to pop anything. He can just access it directly as memory, right? He's not going to pop his values off the stack when he's using them. Okay? He's going to preserve this as his current active context. So the top of the stack is being used. And you can essentially just think of this as a stack of function contexts. Because when I return, I'm returning to the previous function's context. So now let's say he returns. Now he picks up the previous function is now top of the stack. This whole active region here is active. And he's got his previous context from when he went down. Right? When he goes down, he tells you where to return to, his return address, and he has all of his information still stored on that location in the stack. So the call stack is basically a stack of context for all the functions that are active or in progress within the stack. They paused and they're going to return back up to them and resume them. So that is what the stack essentially is. Now, when I return back up, I don't clean this stack off. All the data that I put onto the stack, the return addresses, everything like that, it's just sitting there. That's why if you declare a new variable in a function and you don't initialize it, it can contain garbage. It just contains whatever scratch data. It's like this. It's like if you had your scratch pad at the grocery store and your scratch pad had all these information on it, right? So you flip backwards in your scratch pad when you're done. You don't go to a new page. You reuse all your pages, essentially, in your scratch pad. So if you had your grocery list, you cross them all out, but all that data and crossed out information is still there. So when you're going to go somewhere else and reuse your scratch pad there, if you don't erase things and put new data in there for you to remember what you're currently doing, you're just going to look at the old grocery list. Like I say, you're going to reuse it for a new grocery list. You'll still have the old grocery list there. So unless you erase it and replace everything in there, you're still going to be running off of accidentally using some of the old information, some of the old context. So essentially, your stack is a stack of contexts, right? So, and it's also your scratch pad for that. So, again, while it's active, it's your context. When you're done, it was a scratch pad. So you don't care about it anymore. You just don't use that information. And so that is the basics of the stack. And it's the same thing, right? So whenever I come down, whenever I turn back up, if I don't return to the right context or something's corrupted, like you do a stack overflow, you overwrite the return address. You know, essentially it's like these are telling a story here, right? And this guy needs to remember the rest of the context to continue. And if you give him something else back, he's not going to know what to do. He's going to operate incompletely and give you some wrong data back. In fact, if you don't even tell him to return to the right place, he'll be all messed up. It'd be like, if someone's telling you a story, in the middle of the story, they just lost context of what they were doing. Complete context. They would just start saying gibberish. Saying like, I went down to the grocery store to buy some groceries, and then car, road, truck, telephone pole, highway, fish, whale, dolphin, ocean, rock, sand. They wouldn't make any sense. That's what happens when your program goes off in the weeds. If you corrupt where you're going to return back to, you essentially just go off into the weeds and execute a whole bunch of nonsense. It's the exact same thing. You just lost your context. So,
All right, so we're going to go through a very, very simple example. I put it in assembly, but I put some C comments on the side. It's extremely simple. Did it in assembly so that it would be very straightforward, because you have to look at the assembly in order to see the stack. And secondly, because then I don't have to worry about compiler authorizations or turning anything off, try to make sure that it doesn't not compile in these functions or inline them or something. So let's go through this function very simply. So as you can see over here, we're going to call an API called multiply and add. It takes 3 numbers. And what it's going to do is the same thing we did on the board. It's going to take the first 2 numbers, add them together, and then the second number, multiply it, which means we should get 20 plus 10, 30, times 2, 60 is the expected answer. Then we're going to take, so the return value is going to end up what we're going to call x here, but x over here is this REX. It's going to be passed around. So, and RCX is the first parameter. So we're going to take x essentially, put it as the first parameter to add 3 numbers API. And it's going to add A, B, and C. So essentially we're going to get 60, add it to 10, add it to 6, and our output should be 76. And in fact, we're even going to do a printf here. Printf, the final answer is %ix. Okay, let's take a look at multiply and add. So multiply and add, it's going to save. We're going to declare a local variable int c, and then here, essentially, we are doing z is equal to c. So we're saving c and z. Then we're going to call an API called add 2 numbers, and we're going to add a and b, and have the answer come out into x. Then we're just going to return the multiply of x times c, right? So, and then we have the API of add 2 numbers. Essentially, it's just going to be z is equal to a plus b return. Then we're going to call add 3 numbers and so forth. So we'll get to those. Let's just save that. Now we're going to come over here, build this. We're going to run this into this debugger. And we'll set a breakpoint on the startup function. Go. So here you can see we have the return address, right? If we just do a stack trace, we can see. And the return address is here. We're going to allocate one variable on the stack here, or one location on the stack. Okay. And as you can see, now we have that stack location reserved. And so that's now part of our Scratchpad context. Now we're going to put the parameters up. So now we have the parameters to multiply and add. So don't worry where they went, who cares? All you care about is this is what we just did. We put these parameters ready for multiply and add to work. Okay. Now this is the part where we want to take a look at. Now we're going to put another stack location. So again, if I do DQS of RSP, that's actually the stack. And L3 means 3 locations. So as you can see, this is our return location back to the stack, or back to the previous location where we were going. So as you can see, main CRT is the same thing as you can see here. Now we're going to call multiply and add, and we will return to that location. So that location goes on the stack, because that's the immediate instruction after our multiply and add. So we're going to, sorry, I had to stop for a second there. I wanted to check to make sure that you could see my mouse cursor, because then it would be confusing if you couldn't. So, where were we? So then we were talking about the return address, return there, and that's on the stack. So this is part of the context that we need to save for the previous function. Now, it technically is within the memory range of the new function. Now, I didn't even allocate the correct stack space about this stuff. This is all just hacked up. When you go through the calling conventions, it'll actually show you how you're supposed to do all this stuff. But this isn't the correct 64-bit calling convention, because I didn't reserve any stack space for the function I'm calling. Ignore that. So we are now inside multiply and add, and we're going to allocate our variable here. All right, so if we come down to multiply and add, as you can see, we would do a z variable. We save a z, and we put c, which is the third parameter. The third parameter was 2. Okay, so let's watch that happen. So we do this, DQS RSPL3. As you can see, we now have this location as our z variable. Now we're going to take R8, which is our third input of 2. We're going to put it into our local variable. Now as you can see, there it is, 2. Now we're going to call add two numbers. Add two numbers are going to add their own space there. Now I want to take a look at this here. So as you can see, we want to return back up to add and multiply, right? Just like before, because we're in add and multiply and add, and we're going to call add two numbers, but we want to resume right there. Okay? So that's what we have here. And we can actually take a look, and it is XOR RDX, RDX. And we have this location here. Now, if we look into what this add two numbers does, it also has its own int z, and it essentially is going to put the addition of the two numbers into that z. So let's take a look. We're going to do the add. Okay. So 1e, we did the add, right? So 1e is 30, which is what we would expect from 10 plus 20. Okay. So oops. So as you can see, 10 plus 20 is 30. We got 30 in our z variable, which is what this RSP is pointing to, and what's on the stack. We're going to put it into REX, which is our return. Yeah, who cares about that? Doesn't matter, right? And so now we returned, and look, we're at their location, and we cleaned up the stack, right? So we cleaned up the Scratchpad place for that previous function, and their return address is no longer on a stack. But again, if I look down, let's do 20. Yeah, if I look down 20, look, that's still on the stack. The return address, still on the stack. Even though our current stack is here at the 2. That's where our current stack is. This is all free to be used memory by the next location. So this is why, again, if you declare a local variable and you don't initialize it, you just use it as is, you're going to get some random data. It could be 0, it could be 1e, it could be this old return address. You know, because whenever new functions get called, they also only overwrite what they need. And not all functions take all code paths. So you have garbage from who knows how many function calls ago. So let's continue here. We're going to do this multiply, who cares, right? And so it's 60, right? And that's what we would have expected on this first function call, right? This first function call, we get in there, we get 60. Now we're going to add 3 numbers. And we're going to pass 60, 10, and 6. And 60 plus 10 plus 6 should be what? 76, right? Okay, well, let's take a look here. So, okay, we're going to call this function now. Now here, let's look at where we're at now. RSP L3. So now we have this location because we're going to return back to where we were going, right, to continue on this thing. And now we're going to reserve 3 locations on the stack. Yeah. Now I know we only have 2 variables, and since I'm packing this thing up, I probably could just reserve 2 spaces, but you're supposed to keep the stack aligned at a certain offset. That's just why I did it, but ignore that. We got 2 variables here. So now if I dump the stack after I allocated them, what do I see in it? Whoa. We see this old return address, we see a number 2, and we see a 1e. So our current variables are going to have garbage, or depends on where we put them, but they already have garbage in them, right? So as you can see, we're going to put C. That's what this is doing here, move R8. So here we're going to do Z is equal to C, essentially. So we're putting Z in there. And so now Z has 6. Z has 6, right? So 3. So as you can see, we've already overwritten the 1e with 6, which is in there. And then we're going to add those with the first entry. So it's A plus C, right? That was 60. So now we have 482 hex in here. 482 hex is 66, right? And so the middle variable, remember we passed in up here, was 10. And that will be in RDX, right? So now look what's happening here. We're taking the middle variable and we're adding it to a variable. Let's see here. What do we have written out here? In this last function here, we have y is equal to y plus b. But what happened? There's no initialization of y. And so depending on where we put y, we're either going to have this number or this number. But plus 10 here, or plus 16, is 2. So this is what happens when you reuse a variable. When you use a variable without initializing it, you just get whatever garbage left on the stack, which is like it was just 2. But we could have had this number if we would have allocated the variable to use that location. So now we're adding essentially RDX, which is 10 plus 2. We're going to get 12 now, and we're putting it in there. So we got 12, right? So, and now we're going to move the value of 66, and we're going to add it to 12. And we got 78 now. So now we actually have the wrong answer. because we're just getting the garbage that was on the stack from the previous function call. And so now we're going to clean up the stack here, right? We're cleaning up our scratch pad. This is our scratch space that we had for this function right here. All right. And this is technically part of our scratch space, but it's a reserved location that's storing context to return to the previous function, because we also do get some of the stack up here sometimes reserved for parameters. But and sometimes we also save other context information because there's a volatile versus non-volatile and stuff like that. But that's all part of the calling convention. That'll be the calling conventions video. So you do have pieces of stack or pieces of context from the previous location saved within your own context, but forget that for now. Essentially, the simplest thing is just to think of that we removed our scratchpad space, right? And now we're back to the original scratchpad space. And if somebody wants to, at some point go down the stack again, they're going to end up with these stuff, all this garbage here. And of course, where we didn't go and do anything, we still have some zeros in there. But where we did go, for example, these things up here, we do have some garbage on the stack. And of course, now we're going to do our little printf thing. And our printf is going to say final answer is 78, which of course is incorrect because we use an uninitialized variable. And instead of just taking b so that we can add it to z, we added the uninitialized variable to b and then added it to z, which contained the first two. So this function here, of course, doesn't do what it says. And by using the uninitialized variable, it messed things up. And so that's essentially a representation of how the stack works. And we just exit process, who cares? So that is pretty much it.
This is the basics of the stack. And so with that, the more advanced video is the calling conventions video.